Good morning, my name is Ward Abdelkader. I'm an assistant teacher at Ibn Khaldun University in Algeria. It's my pleasure to participate in this conference. In this presentation, I will share with you a part of my research entitled Moving Database Cost Model from Darkness to Light. So the outline of my presentation is given as first introduction, second context and motivation, then our solution, and finally we end by conclusion and some remarks. Let me start with some general information about a database lifecycle. As you know, a database lifecycle is a process that begins from requirement, conceptual design, logical design, and physical design. These phases are based on metrics and rules to quantify the quality of each solution to optimize the performance metrics. At the level of physical design, the database administrator actor face many challenges of what is deployment platform to choose, what's physical structure to choose, how to tune and control a database system, and so on. Usually, these problems are driven by database cost model in the physical design phases. So, what is a database cost model? A cost model is a mathematical function assigned for each operation and the parameters and metric value. Operation is a relation algebra operation like join, scan, sort. Each operation depends on algorithm implementation like hash join, programmation paradigms like MapReduce, and emerging hardware like new storage device and the processing device. Parameters depend on the database life cycle phases: requirement, conceptual design, logical design, physical design, and deployment. A set of metrics quantify one non-functional requirement like AU cost or CPU cost. Let's consider the following example that illustrate a cost model calculate response time of join operation in SSD hard disk. The parameters of this cost model are mapped on the layer of database system as shown in this figure. Now, where can we find the cost model? We realized that the present cost model in the literature is huge, sometimes well explained, otherwise drowned in the paper explanation without discussion of parameters and formulas. Actually, so if you need to survey a database cost model domain without consider posteriori our solution, you must collect scientific information, manage the information collected, watch, monitor, and keep regularly informed by the new information. So the scientific researcher face challenges such as what is the cost model are more appropriate for a given context? How did the database cost model evolve in the physical design phases through time? How can classify the cost model per topic, per years, and looking how can be related? So the challenges here we need a survey of database cost model evolution. In the actual process, to search a cost model, a researcher must use a service index like DBLP and Google Scholar. When we browse the Google Scholar using the keyword database query cost models between 1917 and 2018, we found around 313,000 and 800 results corresponding to cost model, which represent a huge number. This data will be dark data due to the spectacular evolution of database technology, which cover database models from relational to graph, platforms, database system, and processing device. This situation complicates the exploitation, reproduction, and the reuse of existing cost model to provide the reader a good review of the topic, because it's difficult to see how cost model entities are related from the scientific papers, as cost models become an obscure entity. Hence, the problem statement of the research question is how to increase the survey papers of cost models related to the evolution of database physical design domain. From this, we can identify these problems. A variety of database cost models. Relevant information is rounded in the scientific papers. Usually, authors express the revision and the evolution of cost model using natural text notation. Searching how cost model is adapted is manually costly and time-consuming process. The case of digital libraries like DBLP and Google Scholar helps in the scientific papers by providing information like authors, papers, committees, and topic. But for instance, one can only consult a cost model in order to see its chart, its signature, and its components. He needs to find their respective scientific papers, selection, and compare them manually. For a monitoring survey of cost model evolution, there is no tool of database cost model survey to accurate the big picture and the mental image on the relationship between cost model. This motivates our investigation to assist the survey of the evolution of database cost model domain. Our objectives. As illustrated, we aim to move in database cost model from darkness to light to see how cost model entities are related. Our goal is to provide a comprehensive survey process of database cost model. This is important because orienting users to easy survey of cost models, helping researchers to compare and analyze their own cost model, and decrease the difficulty related to the constant evolution of database cost models domain. To solve the problem, we have proposed an approach of 4 sequencing phases. First, raw data, scientific files, papers are collected. Second, data processing, categorizing the cost model changes and analyzing the relation between them. After graph database, the data is stored as a graph model from the cost model evolution. And analytic side, the data is accessible to reporters as a network visualization. We have reviewed the scientific papers, then studied their contribution, examining the acceptance of different database cost models. To study the changes, we need different versions of cost models. We summarize the categories of change that push the researcher to revisit the cost model defined in the past. In our analysis, we consider the following categories of change: calibrate or more expressive the cost model, extending cost models by integrating a new dimension like energy consumption, revisited a cost model and building them from scratch, and cite or use an existing cost model in several applications of database physical design. For example, the author here in this paper looks the cost model proposed by Monigold and extended it to integrate a new SSD requirement and define a cost model that captured the interaction between two physical design index and data partitioning in order to estimate the IO cost. To take easy the analysis of cost model relationship, we have proposed a graph model from the cost model evolution that matches the needs of the scientific researcher. These graph models model and store the relationship of cost model. The cost model survey graph data model consists of 5 node types: cost model nodes, scientific research, manifest node, context node, author node, and the conference nodes. 2 cost models are linked by 6 relationship types: cited, extended, used, revisited, and calibrated. We look at the cost model survey as a direct graph with a set of nodes and a set of relationships. In our graph model, cost models are represented by a nodes with label cost model. For each cost model node, we store the information parameters and the paper references. For the cost model researcher, manifest is defined as the partial set of cost model to formulate a different research questions. A researcher needs to answer several research questions to get value from data and relationships. Our proposal has been implemented using the Neo4j and the language query cipher to explore the content of the database graph. As you can see in this figure, we have 2 parts, integration side and analytics side. In the integration side, each database cost model paper has a context and a relation type with the other cost models. The context must be extracted as a summary. During this process, we will start by the text parsing of the scientific papers using dupe solution to identify the cost model context. In this step, we will use the natural language processing techniques of the text modeling known as a bag of the word model to generate the context of database cost models. There are possible errors that make the context incomprehensible because of the limitation of the berg of the word. This case is very long and a complex task. For the best version of our proposal, we have limited our implementation on the analytics side of our proposal. We have provided a manual solution to enhance the database by several examples and data of database cost models with its context and its relation type. In our implementation, scientific researcher manifest is translated into a cipher query that manipulates the underlying Neo4j graph and reporting the result with visual analytics. We have considered 4 easy scenarios of exploration: finding cost models for a given context, visualize how the cost models are related and trace their evolution, clustering the existing cost model based on criteria, and cost model recommendation. Let's consider the following example that the researcher come up with a manifest to find all cost models of a given context. You can see an example of the graph query cipher language to get information and return the cost model ID, name, and reference paper that match the context with details informations. This figure shows the group of cost model evolution history that contribute on the same research objective. These cost models contain information about versioning and its evolution with 6 kinds of relationship: cited, extended, used, revisited, and calibrated. We believe that I will be a helpful tool to better understand the research trend and its evolution over time. The third use case shows the clustering of existing database cost models using GraphX Apache Spark API. In this figure, cost models are classified according to the database source. Each cluster is subgraph. Here we get 4 clusters: cost models from relation data source, object data source, XML data source, and a cluster for cloud database. In the last use case, using pattern matching with cipher make graph-based recommendations. We want to provide recommendation for cost model that a researcher has not found. For instance, we can use our database graph for a cost model to recommend similar cost model by using machine learning techniques to get a similar cost model proposed by the author legibility. The advantage here, you can use KNN recommendation inside a declarative cipher language. At the end, to summarize, I have presented a database cost model. I have noticed that survey papers of cost model related to the evolution of database physical domain is difficult. As solution of problem, we have proposed a graph model of cost model evolution as database graph. This graph model using for sharing, analyzing, and clustering. Also, this graph enhances cost model by providing context. And we'll have proposed a proof of concept of our proposal. In the future work, we must extract the context from the scientific papers by using deep learning solution. Thank you for your attention.